Good evening, everybody. I hope all of you are doing fine and well and ready to start a new lecture today. Any doubt from the last class? Though I need to explain to you the coordinates of tetrahedral and octahedral hole in HCP, and we will allocate some time for that, even though it's not that the exam questions will come from them, but unless I feel if I'm not able to explain you that the purpose of the course is not achieved, because this is where most of the textbooks actually leave you. So we'll do that definitely. Other than that, if you have any query or anything, just post in next 30 seconds, else we will start with the new topic. So while you think, if you have any doubt, I will just go through what we did in last two classes, or rather last 1.5 class. We talked about the basics of solid state chemistry that involve unit cell, crystal system, lattice type, close packings, some common structures based on both cubic close packing, AX and AX2 type, like rock salt, fluoride, antifluoride, cesium chloride type, and based on hexagonal close packing, which is nickel arsenide, then wurtzite, zinc sulfide, and titanium dioxide and CdI2, and also CdCl2, which is again based on cubic close packing. So this is what we have covered today. Now, I have two options right now. We can go to complex structures, not rather complex, but a little more than what we have read till now. Perovskite, pyrochlore, then superconductor, ordered perovskites, or spinel, or we can discuss some concepts. So I generally think that we'll take a very small break from doing structure, do some concepts, and then come back to structures again. Okay, so this is how we will proceed. I take that you don't have any doubt. So we'll start today's lecture. Okay. So we study about crystal structures, right? This particular thing adopts rock salt structure, this one adopts fluoride structure, this one adopts anti-fluoride structure. What are the various factors that influence, that tells a particular compound to crystallize in a particular structure? What are the various factors that govern that thing? So even though to exactly chalk out all the factors and to say, okay, these are the set guidelines which will follow. There is a flow sheet. If you have this, go to this. If you have this, go to this. Even though no such thing exists, but still there are certain rough guidelines that will help you to make a good, fairly good guess up to like what structure your particular material will adopt. Okay, so first of all, that goes without saying that the structure adopted by the compound will depend upon the formula of the compound and the valencies of the constituents, right? Very, very simple thing to imagine and guess. If it is AB, it can adopt only an AB kind of structure and not AB2 kind of structure or AB3 kind of structure, right? If it is an AB2, it will adopt an AB2 kind of structure. So that kind of narrows down to what our material, what structure will our material adopt. So first and foremost, and the most simplest one is it depends upon the formula of the compound. Rather, I would say it depends upon the stoichiometry of your ions in that particular formula. Second is bonding. Now, how is bonding important? If you remember when I told you about the rock salt and the zinc blend kind of structure, where rock salt has 6 is to 6 coordination number and zinc blend has 4 is to 4 coordination number. I told you that more ionic compound tend to adopt rock salt structure, even though both are 1 is to 1, right? And a little more, little less ionic will adopt the zinc sulfide structure. Why? Because as we'll study in next few slides as well, in case of ionic compound, the ions tend to have as high coordination number around them as possible. Similarly, I tried to find it a lot, and I found it at only one or two places, and I'm sure you would not have read it. What is the difference? What is it that prompts some material to adopt only hexagonal close packing and some material to adopt CCP? Right now, we just discussed the difference between why a particular compound will have NaCl and why a particular compound will have zinc blend kind of structure, even though both of them are 1:1. But then we could talk about the difference in coordination number. Now, when I talk about HCP and CCP, the coordination number in both cases is 12, right? Then why is it that HCP, some compounds, nickel arsenide goes take HCP packing, and rock salt NaCl goes CCP packing? This is because in your HCP packing, the metal to metal distance, let's say if your metal is occupying the octahedral site in the closed packing, the metal to metal distance is smaller in case of HCP as compared to that in CCP. So if your metal is more electropositive, the chances of repulsion between 2 would be more in CCP. Sorry, in HCP. So they will adopt a CCP structure. So more electropositive ion, highly charged ion, they will tend to adopt CCP as compared to HCP. So what it brings to this thing, the kind of bonding, whether it is ionic bonding or whether it is covalent bonding, that also governs what kind of crystal structure your compound will adopt. Then the size of atoms and ions. There is this thing, a compound, let's say I have a particular composition A2O3. Even though this will not fall into the scope of this particular course, but just giving you an example, this A2O3 can have C-type structure, which is also called Bix-biide structure. You will not study this one, but I'm only giving you an example. Okay. And it can also adopt ilmenite structure. And a particular ilmenite compound is FeTiO. Okay. There's some problem. Okay, so my point is, even though the stoichiometry is same, what happens is that when your ions are bigger, they go to Bix-biide structure. And in fact, Bix-biide is a structure adopted by all your rare earth oxide, lanthanum oxide, gadolinium oxide, then dysprosium oxide. And ilmenite is a structure FeTiO3 when your ions are smaller. Okay, so size of atoms and ions also are important. Now, size of atoms and ions are important, and then their relative sizes is also very important. When I say relative size of cation and anion, and that many of us have read in terms of radius ratio rule, and we will discuss it a little more in next few slides. So as I said, the various factors that influence a crystal structure are the formula of the compound, that is the stoichiometry of the cation and anion, the bonding, whether it is more ionic, whether it is more covalent, size of the atoms and ions involved, as well as the relative sizes of the cations and anions. Okay. Now, when we say the structure, as we mentioned, a structure, an important part is the coordination number of cation and anion. Okay. So most of the time, if we also understand that what are the coordination number preference of your cations and anions, then also we can guess the structure. Now, what does the coordination number depends on? It again depends upon the formula of the compound. Let's say if I have a compound AXBY, then coordination of A and B, that is how many B's are surrounding A and how many A's are surrounding B, that will be the ratio, that will be in the ratio Y by X. That is, if your A ka constant is X and B ka amount is Y, then their coordination will be in the ratio y by x. Okay. Provided, now this is an important thing, provided that in your compound A is only bonded to B and B is only bonded to A. That is AA and BB direct bonds are not present in the compound. For example, in NaCl structure, Na is only bonded to Cls and Cls are only bonded to Nas. This is what I want to say here. So if I take few example, in a AB2 compound, the coordination number of the will be in the ratio 2:1. That is, the coordination number of the A will be twice that of B. A very good example is calcium fluoride, the fluoride type structure. The ratio of calcium to fluorine is 1:2. But the coordination number of calcium is 8 and fluorine is 4. So the ratio of the coordination number is 2:1. Okay. 8:4, that is 2:1. Similarly, NaCl, their X and Y are 1:1. The coordination number of both Na and Cl are 6 and 6. They are in the ratio Y by X, that is 1:1. Okay. Now, you always do not have only binary compounds. I mean, your formula does not have only two cations or two ions, I would say. It can also be a complex, it could have more than two ions. For example, perovskite, AbO3. So if the formula of the compound is AX, BY, CZ, now here your C is an anion. It could be fluoride, oxide, hydroxide, sulfide, whatever. In that case, if we have to guess the coordination number of one ion, let's say we know the coordination number of one or two ions and we want to know that of the third ion. In that case, the average cation coordination number, the cations here are A and B and C is your anion. So average cation coordination number and average anion coordination number, their ratio is in the ratio of Z, that is the number associated with the stoichiometry associated with C upon X plus Y. That is sum of the stoichiometry of the cations. Okay. That means I can say that average cation coordination number into X plus Y would be Z into anion coordination number. Now let us look at another thing. How can I define average cation coordination number? I can define it as X of coordination number of A plus Y of coordination number of B divided by X plus Y. This is a simple average ratio. Now from here, average cation coordination number into X plus Y is X into coordination number of A plus Y into coordination number of B. So if I put it here, X into coordination number of A plus Y into coordination number of B, it would be Z into coordination number of C, that is anion. Now, not now, but when we will do the structures of perovskite and all, we will try to verify this particular rule. Okay. Most of the time, why this, I'm talking of this particular relation, because it is somehow easy to visualize. Let's say in perovskite only, if I take calcium titanate, it is easy to visualize how many oxygens are surrounding my calcium and how many oxygens are surrounding my titanium. But most of the time it is difficult to visualize the coordination number of anion, and that is where such empirical relation they come into head. Okay, now let's talk about the nature of the bonding. We talked about ionic and covalent. See, the rule is simple, ionic solids will try, here suppose I'm talking of a cation, it will try to have as many anions around it as possible. Why? Because it increases the electrostatic force of attraction. More the electrostatic force of attraction, the stable the compound would be. Okay, but what happens is that now, okay, let's just talk about this ionic solid. So what from this point, what we try to say is that ionic solid will tend to have as high coordination number as possible. All right. But when we talk of covalent solid, the covalent solid normally, because they are the sharing of electron cloud. So covalent bond, otherwise also we have read in an inorganic chemistry, they are more directional bonds. And the atoms, they generally have preferred coordination environment. That means either they would take two or they would take three. There is no concept of electrostatic attraction. The energy getting stabilized by more decrease of energy due to electrostatic attraction. So here the coordination numbers are rather small. And this particular actually shows up in the structure. I'll give you some example. Barium oxide, strontium oxide, and mercuric oxide. The three cations, barium, strontium, and mercury, they have kind of similar ionic radius. Okay, and stoichiometry here is also similar. They are 1:1. But barium oxide and strontium oxide, they adopt the rock salt structure, which is the NaCl structure. Now here the coordination number is 6:6. But so based on size consideration, even my mercuric oxide should also have adopted the rock salt structure. But it has a structure wherein you have oxygen, mercury, oxygen, linear segments. These linear segments are more closely bonded than their bonding to other segments. So this is how the covalency effect show, because mercury ion is tends to form more covalent bond as compared to barium and strontium. Now coming to this very simple series. Aluminium, going down the halogens, aluminium trifluoride, aluminium trichloride, tribromide, and triiodide. Now, what is happening down the series? The anion is becoming larger. The anion will have more polarizability. The covalency effect in the bond will increase. So, what happens is the effect is seen in their crystal structure. And how is that? Aluminium trifluoride forms distorted an ReO3 type structure. We will talk about ReO3 type structure. It is basically a crystalline structure formed on cubic close packing. And because it is a crystalline material, it is a high melting solid. On the other hand, AlCl3. You remember what was the cadmium chloride structure? We said chloride ion forms the CCP, and cadmium ions occupy octahedral hole in the alternate layers. So every layer in between is empty. Okay. So that means it is partly ionic, partly covalent. So AlCl3, which has slightly higher covalent character as compared to AlF3, or I would say lesser ionic character as compared to AlF3, adopts this layered structure. Coming to further bigger ions, bromine and iodine. Now these are highly polarizable ions. They have a covalent effect in the bonding with aluminium. So basically they exist as molecular unit with Al2X6 formula. And not that I cannot describe their structure in form of based on close packing. I can still do it. For example, if you look at this right hand figure, okay, the packing of, I'm talking of AlBr3 now, which actually exists as a dimer Al2Br6. But in solid, I can still describe its structure as a based on close packing. But it is a loosely close packed structure. How? The bromine ions, they form the hexagonal close packing. Okay. You can see that the dark circles are the bottom layer and the shaded circle are the second B layer on top of it. Now, so if I try to give you, and of course, the bromine forms the hexagonal close packing and aluminium occupies the tetrahedral holes. Okay. 1/6 of the tetrahedral hole. That you can work out. For every bromine, you have 2 tetrahedral hole. And for 6 bromine, you will have 12 tetrahedral hole, but you need only 2 aluminium. So only 1/6 of tetrahedral holes are occupied. Okay. Now, how is this associated? You try to relate this figure to this figure. Now, this is my aluminium Br6 unit. Okay. Consider this is your A layer and consider this is your B layer of bromine ions. 1, 2, try to relate 1, 2, and because A and then 4 and 6. These are bromine A layer. Sorry, this is B layer and this is wrong. This is actually C layer. So A and C layer of bromine are staggered. Bromine atom 1 and 2 are lying directly over 4 and 6. And bromine atom 3 and 5 are on the voids. Okay. So now what happens is I can describe it. The position of bromine can be described as this hexagonal closed packing wherein your aluminium is occupying tetrahedral hole. But in nutshell, if we see this, basically the strong bond exists only between these bromines. So that means each bromine belongs to exactly one molecule of Al2Br6. Now, bonding of this bromine to the next bromine in HCP is rather loose. And why has this happened? Because of covalent effect in the bond, the ions tend to have lesser coordination number. They have lesser tendency to go three-dimensional in their bonding and periodicity. Okay, effect of size. Okay, now we will just don't look at the screen, look at me. What is the effect of size? Now, as I said, in case of your ionic solid, your ions, because of stability that is endowed upon it by electrostatic attraction, it will tend to have as many anions around it as possible. Okay. So as your cation, and one thing is there, it can have as many as possible. Now there is another factor. The more it comes together, what happens is the light charges, there will be repulsion between the electron cloud, which will also tend to make ions a little farther apart. So both these factors are acting in opposite direction, and the result of this is that the ionic compounds adopt as symmetric structure as possible. It tries to gain as high symmetry as possible in their crystal structure as compared to the covalent compound. Okay, so this was about the effect of size. Now coming to the radius ratio. How does the radius ratio thing actually come into play? Now what happens is that your cation is surrounded by anions. Okay, and as I said, it wants to take as many ions as possible around it so that it gains more attraction and more lowering of energy. Okay, now anions can touch each other, but as this cation start expanding, it can adopt, the anions will start, becoming farther in distance from each other. And at some point, it might happen, it will come to a point where now the cation is so big that it can it can actually position more anions around it. Okay. So we say that beyond a certain limit, now its coordination number can go higher. Similarly, it can keep on increasing, and then it will reach another end where now it can take more number of ions around it. So there is a limit of radius ratio beyond which the coordination number can increase. Okay. Now I was talking about the higher limit. But one thing that I must tell you is, you just look at these structures, the three configurations that are mentioned here. This is stable, okay, when your cation has, let's say, here it is 4, it could be 6 also, it could be 8 also. When your anions are not touching, they're touching cation, but they are not touching each other. This configuration is stable. The second configuration, wherein your cation is touching the anions and anions are also touching each other, that is also stable. But when a situation happens that the cation is becomes small, very small for a particular coordination, again I am showing 4, it could be 6, it could be 8, it could be 3, but now cation is smaller than that void. That is, it can rattle in that void. This particular configuration is not stable. Okay, so this condition sets the lower limit of the coordinate of any particular coordination number. Below this coordination number is not stable, so the cation will have lesser number of ions around it. यहाँ 4 पे ये stable नहीं है तो वो अब 3 लेगा. And the fact that at some point it becomes so large that it can now take extra anion sets the higher value to the radius ratio limit. So between these two limits, we can have a particular coordination number, and this is what we mean by radius ratio rules. Okay. So, right. So as I said, radius ratio rule, as the size of cation increases, it can pack more and more anions around it. The guidelines are that cations must be in touch with anions. That sets the lower limit. Cation must not rattle within the hole. That is an unstable configuration. Anions may or may not touch each other. Okay. So with these guidelines, we can set a limit for the radius ratio for a particular coordination number. Okay, I hope this is clear. So this all of you know, I just wanted to explain you the concept behind it. Numbers anyway, we have been reading since from our BSc days. So when our radius ratio lies between 0.15 to 0.225, it is a triangular, it will generally tend to have three anions around it. Okay. When it becomes more than 0.225, now cation is big enough. It can take one more anion and it can form a tetrahedral coordination around it. When it goes, and this can happen up to 0.414, it is increasing in size. Beyond that, the cation becomes higher, larger in size. It can take two more anions and you can have six. And then from 0.732 to 1, you can have a cubic coordination number. I'm sure all of you noticed that coordination number 5, coordination number 7 are missing. So what is the reason behind it? That is because when we are talking, now these radius ratio are for the symmetrical structure. And let me remind you, like in humans, like in us, we have imperfections. Like in things, we have imperfection. Structures also have imperfection. But we are talking of the ideal cases. In ideal cases, if we have, let's say, coordination number 5, okay, now assuming that all your cation and anion bond lengths are similar, okay, which can happen only in tetrahedra and octahedra and cubic, you cannot form a space filling configuration. If you have a tiles, that is why I'm sure you will never would have observed on the floor of your house or wherever pentagonal tiles don't exist, because they cannot form a space filling configuration. You will have empty space between them if you try to close pack them. Okay, that doesn't mean that your structure or your molecule cannot have a point symmetry of C5. It can have. I'm talking of the space symmetry. So given the condition, अगर आप cation anion के bond different कर दोगे तब possible है कुछ भी symmetry. But given the condition that all your cation and anion bond lengths are constant, you cannot have a coordination number of 5 in closed packed structure. I hope this is clear. Okay, so 5-fold, even if it exists, it makes distorted structure, which is perfectly fine. Nature is full of structures which are distorted. All right. Okay. These are just few examples. Whenever you go back to YouTube, you can check these examples. The radius ratios are given, and then based on that, the coordination numbers are predicted and it is compared with the observed. Okay. I've taken this table from AR West. Now, limitations of this. As I said, A, this is all for the ideal condition. B, every rule has got certain limitation because there's nothing in this world that is ideal, right? Okay. Limitation is, now when we want to calculate the radius ratio, that is R cation by R anion. I hope I didn't mention it in the beginning, but let me now mention it. When I say radius ratio, by convention, it is smaller ion by bigger ion. And most of the time it is our cation which is smaller. So we say Rc by Ra. All right. Now, now when I'm calculating my radius ratio, I'm actually taking the ratio of the ionic radii. But the ionic radii themselves will vary depending upon the source that we are taking the ionic radii value from. Okay, there are Pauling's ionic radii, another ionic radii. For example, if I'm sorry, this is not rubidium. Okay, it could be, yeah, it is rubidium iodide, and this could be the radius of iodide. Now, rubidium iodide, if I try to calculate the radius ratio, it has 0.69 when I take the radius of iodide as this, and it has 0.80 when I take the radius of iodide as this. And both of them fall in the different range. This falls for the cubic and this falls for the octahedral. So different coordinations are predicted, right? So we have to see which source we are referring to. Yeah, whatever paper we are referring to, what source have they referred to? So these kind of anomalies happen. Second, the radii will actually differ whether given the if whether the molecule the your particular ion is existing is in a covalent compound or it is existing in an ionic compound. Because how do we calculate the ionic radii? We calculate the radii. Normally, we do a single crystal XRD. We try to find the electron density map between the cation and anion. We measure that distance and we halve that. Okay, depending on what is our bond, whether our bond in that particular structure is longer or it is shorter, the ionic radii value would change. Okay, so it depends upon what kind of compound the radius has been measured. Also, I'll give you a reference. There is something called, most of you probably know also, RD Shannon. This is where I take my ionic radii value from if I have to do some particular calculation. There, when he mentions the ionic radii for a particular ion, he also mentioned what is the coordination number. Okay, because if my cation is surrounded by 4 anions and I calculate the distance between cation and anion and halve it, then in 4 coordination, this distance will be smaller than in 6 coordination because 6 anions around the cation would be spread wider. Similarly, 8 anions around the cation would be spread still wider. Okay, so the ionic radii themselves are the function of coordination number as well as the nature of bonding. So these are the things that kind of bring anomaly, but it is fine. With this anomalies also, this particular rule, the radius ratio rule, has gained, it is quite helpful to when we are doing the blind guessing and all that. Okay, now borderline radius ratio. Sometime because we defined, these radius ratio. But what happened? As soon as I become 0.226, my ion decides, no, now I will not have 3, I will have 4. As soon as I make it 0.415, it decides, now I'll have octahedral. No, it doesn't happen. Beyond, I have this fixed value, but in a range, in a bracket, in this range, these particular ratios are called the borderline ratios. And this is where we observe that material, your compound now has the freedom. It can decide what it wants to do depending on various ratios. And I, as a solid state chemist who's been working for 20 years, I can tell you the compounds, the cation which show these kind of borderline radius ratio, they are most exciting to work with because now they are sitting on an edge. You can make them fall into this structure, you can make them fall into that structure by varying many things. By varying your synthesis route, by varying your temperature, pressure, external condition. So, not that it will always happen, but these are most interesting to play with. Okay, so what I want to say is that was just a diversion. If you have compound wherein your cations have got borderline radius ratio, they have the tendency to show polymorphism. What is polymorphism? A compound when it can exist in more than one structure. That is called polymorphism. Okay. For example, germanium oxide exhibits both silica-like structure, wherein it has the coordination number of 4. We miss the silicate structures. Otherwise, I would say that SiO4 is the building block in all the silicate structure, and the coordination number of silicon is 4. So, yeah, coming back to this, germanium oxide exhibit both silica-like structure and rutile structure. Rutile is your TiO2, where the coordination number of cation is 6. Okay. Sometimes when your ion is unable to decide, then it adopts very distorted polyhedra also. For example, if it lies between 4 and 6, somewhere in the borderline, It happens in case of polymorphs of vanadium pentaoxide. It will take a square pyramidal kind of octa coordination. Now here the coordination number is 5, but in square pyramidal, all your cation and anion bond lengths are not equal. So what is a square pyramid? It is 4 anions in a square and 1 capping it. So the coordination number of 5 it, and it is a very distorted polyhedra. Okay. Then for similarly ZrO2. Now this is one compound that many of us work with. It's a highly technologically useful compound. Iska radius ratio is 0.68. Okay. For now going to cubic, actually you have to have 0.673. So it is kind of borderline. As I told you, there is a range. I cannot decide right at 0.73 to no, I have to jump to this side. So this particular radius ratio ideally predicts a coordination number of 6, but it cannot go to, it is not happy in 6 because it is very big for being 6, and it cannot go to 8 because it is smaller for being 8. So it adopts a distorted polyhedra where coordination number is 7. The room temperature monoclinic form of ZrO2 has got 7 oxygens surrounding zirconium. That is not a regular polyhedra like a tetrahedra or an octahedra or a cube. All right. So this is one example how you can calculate R plus for R plus by R minus, that is your radius ratio for a particular coordination number. You will find this at many places in literature, starting from the 12th standard books. I would not want to spend a lot of time on it, but I've still done it so that you can refer back to it. And if there is any problem, you're most welcome to call me. Okay. This is for 4, this is for 6, and the same rule is applied for square planar also. Okay. Now the concept of lattice energy. Okay, what is a lattice energy? What's the time? Let's take a 2 minutes break, and please post if you have any questions in the chat box. Any question, any comment? If not any question, any comment, whether you're finding it useful, whether you would want me to raise the level, lower the level, be slow, be fast. I would appreciate any interaction from you. So Gunjan asks, since she has messaged privately, how do we correlate various HCP, CCP packing with the Brevis lattice? Gunjan, Brevis lattice, Brevis lattice actually gives you, we can do that, but this involves a little higher level of crystallography and a little out of scope of this course. But I will definitely, when I will tell you about this HCP coordinate, I will come back to this point as well. I have noted it down and will definitely discuss it given the time permits us. Okay. I'm sorry, I can't handle it in on this platform. It will take some time, which I really cannot afford to do that. But please interact with me, otherwise I'll also try to take up in the class. Okay. Anybody else? Okay, so what I will do is maybe, at the end of my 7 lectures, I'm supposed to take 7 lectures for you. I will give you some 2 to 3 assignments, which will test how much you have understood from it. I will try to make the question not theory type and try to gauge if I could, especially on the points that most of the time I mention, no, this is not mentioned in the textbook. And those kind of things probably I'll try to test, and we'll see how much I have been able to communicate with you, which will also help me to improve myself for the next course, next year, next edition of this course. Okay. So coming back to lattice energy. So what exactly is the lattice energy? Okay. Uh, Lattice energy is, in very crude layman terms, the energy that you would like to break a particular unit cell, break it into its ions. That is a lattice energy. Stronger is the bond, more will be the lattice energy. So, in very, very crude terms, it is actually the measure of how stable your structure is. That particular crystal structure is, okay? So, when we have to define it properly, it is basically equivalent to sublime the crystal into its gaseous ion per mole. That is your lattice energy. What will it depend upon? I just said it is kind of equal to how much energy do you really have to invest to break that structure. It depends upon the crystal structure. Okay. It depends upon, because on the charges on the ion. We will see the derivation also in a little while. But higher is the charges on the ion, more strongly they would be attracted to each other. So it depends on the charges of the ion. And further are the ion, easy to separate them. So it depends upon the internuclear separation. These are three main factors that decide the lattice energy of your compound. Okay, so I will give you a very brief idea how the derivation of lattice energy is arrived at, rather than giving a complete derivation and all. Okay, so what I can do is, if you ask me to determine what is a lattice energy, what I would say is you simply see what is the algebraic sum of all the attractive and the repulsive forces in your compound, in your crystal structure, and you will get an idea. And this is exactly how we will proceed. Suppose I consider two gaseous ions. A little bit of background that you will need is just go back and check. Otherwise, I've taken directly the potential energy when you have two charge ions. Okay. We know that electrostatic energy is given by Z plus, Z minus. These are the charges on your cation and anion. Rho is the separation between them. E's are a unit charge, that is coulomb, and 4 pi epsilon naught. Epsilon naught is a permittivity of the vacuum. Okay. Now we know that this particular U would be negative if I have oppositely charged ion, because it would be attractive forces, and it would be negative, positive for the like charge ion. Okay. Then what we can do is we can actually take one reference ion and see how many attractive and repulsive forces are acting on it. Then we can sum it over 1 mole of the ion pairs, and this should be the lattice energy of the crystal. Simple. Let's try to see. Let us try to take an example of sodium chloride. The easiest and the most favorite structure of almost everybody that I know. Let's say my blue balls are sodium and my red balls are chlorine. Okay. Now you think of, concentrate yourself on this blue ball. All right. I'll rub it so that you are able to see the blue color. Okay. Now, yeah. How many, now this blue ball at the body center, we will just quickly revise our NaCl structure. If I have sodium at the body center, I should also have sodium at the edge centers. That is 12 of them. And then I should have chlorine at face centers and corner. So chlorine forming the FCC lattice and sodium occupying the octahedral holes, which are body center and edge centers. Now concentrate on the sodium, the blue ball that is lying at the center of the cube. If you think its nearest neighbors are 6 chloride ions that are lying at the face center. Precisely this, then top and then bottom, and then this back face and the front face and then left face and the right face. Okay, so it has 6 chloride at the face center, and let us assume that distance is R0. Okay, R0 means between Na and the face center chloride. Okay. Now what is the next nearest neighbor? Next nearest neighbor are 12 sodium ion that are lying at the edge center, which is this which is this, and this. Similarly, 4 in the bottom face, and similarly 4 in the center of this cube, right? So I have 12 sodium ions. Now what are still other next nearest neighbor? This is what we call as NNN, would be 8 chloride ion that are at the corner of the cube. And these would be at the distance of under root 3 R naught. How can you calculate it? If this is R naught, you can actually calculate, if R naught is your this distance. I hope you are able to understand it. If this is R naught, this would be 2 R naught. Okay. So you can actually consider this edge, and then because now for root 2 R naught, basically Na at the edge center, I need to calculate this particular distance from here to here, which is like half of the face diagonal. You'll be able to calculate it. If you're not, I'll come to it at the end of the class. But you take my word for it. These, if I assume that my first neighbor chloride was at R naught, then my 12 Na at the edge center are at root 2 R naught from the body center Na. And then the next nearest neighbors are the 8 chloride at the corner. And further are, उसके आगे के neighbors क्या होंगे? ये क्यूब के 6 फेसेस के साथ जो 6 क्यूब लगते हैं, the 6 क्यूब adjacent to the 6 faces of this cube, उनके सेंटर में जो Na है, those 6 Nas would be, and they would be at the distance of under root 4 R naught. Similarly, we can keep on calculating and calculating. Now what we do is, if I have 6 chloride at the face center at the distance of R naught, it is an attractive energy. And this would be given by, now I'm concentrating only on one Na plus. It would be Z plus Z minus by R naught E square upon 4 pi epsilon naught into 6 and minus. Is that okay? Now, the next nearest neighbor are 12 Na plus at the edge centers. Now this I'm calculating for my center Na plus. So this Na plus would be repulsive. Okay. And my distance is now root 2 R naught. So it will become root 2 R naught here. And then this multiplied by 12. And this is positive. Okay. So this is how I can calculate different energy terms, and then I sum it up. So when I sum it up, because this factor is anyway constant for all the terms, I will take this out, take a minus out, and then I will get, ultimately I will get this number 6 minus, because I've taken the minus out, so the positive term become minus 12 by root 2 plus 8 by root 3 minus 6 by root 4 plus 24 by root 5 and so on. Okay. Now, this entire number which is in the bracket, this is called Madelung constant M. All right. So, now what happens is, I replace this term by M and I get this. Now, you just forget about the N for this moment, and it will be minus M Z plus Z minus by R naught bracket में whatever term I have. Now that was the calculation of the energy for one sodium ion. Now suppose I have 1 mole of ions. I can multiply it by N. Anurag, I just need to minimize. Okay. I can multiply it by N. So now this becomes my expression for the summation of attractive forces. Okay. Now the problem is, as your ions are coming closer, they're lying side by side, right? There will be the repulsion. Now there is an attraction between the charges, but all of them have got electron clouds, right? Whether it is positive or negative ion. The electron clouds will repel each other. Okay. And that particular repulsion term by theory has been determined U repulsion NB by Rn. Now this N is your number of ions. This B is a constant. And this particular value R, of course, is an internuclear distance, and this particular value N is called Born exponent, and it has the value of between 5 to 10. So now your total energy is sum of this electrostatic term and sum of this repulsion between the electron clouds. This is your total energy. Okay. Now, when all of us know from this potential energy diagram that we generally plot that at distance R0, our potential energy is minimum. So what we do is whatever expression we have calculated for U, we differentiate it with respect to R, and then we minimize it for R0. And this is what we will get. You don't need to do it. I just want to explain you the terms on which your lattice energy would depend. And then from this is equal to 0. You can calculate the value of this B. This B you substitute in this particular expression. And you will land with something like this expression. Now you concentrate on this. Okay. Now this is a constant, N is a constant, so I can forget about it when I'm trying to see what are the factors which will affect lattice energy. So my lattice energy will depend upon N, but N also is Avogadro's number, so let us forget about it. M is a Madelung constant, so it will depend upon M, it will depend upon Z plus, it will depend upon Z minus, and it will depend upon R naught. Okay. Now what will M depend upon? I wish we were doing an offline class and then I could have asked you this question. M was, how did M came into being? M came into being by the fact that my ion is surrounded by how many nearest neighbor, how many next nearest neighbor, how many next nearest neighbor. That means Madelung constant is nothing, but it depends upon how your atoms and ions are arranged in the lattice, right? Okay, that means it depends upon crystal structure. M depends upon crystal structure. Z plus and Z minus are the charge on cation and anion, and R naught is the internuclear distance, which will depend upon lattice parameter. Lattice parameter will depend upon ionic radii of your ions forming the compound. Okay, now, so ultimately, as I said, your lattice energy will depend upon M, N we can forget, it is Avogadro's number or number of moles. R, Z plus and Z minus. Now, if I take a particular ionic structure, suppose I want to compare ACl and BCl. They have similar structure. Then my Madelung constant is same for them because it depends upon structure, right? I hope it is clear to you. Now my variables are R, my variable is Z plus, my variable is Z minus. Now, if you see that your Z plus and Z minus, they appear as a product. So this becomes a very important factor in deciding the lattice energy. Okay. Now, what is the implication of this? You consider the same crystal structure, rock salt. NaCl exists in rock salt structure. Magnesium oxide exists in rock salt structure. But given the fact that the charge on magnesium and oxygen are more than Na and Cl, and also the fact that in lattice energy expression, your Z plus and Z minus appear as product. So 2 into 2 versus 1 into 1 for NaCl and 2 into 2 for MgO. For the same crystal structure, the divalent ions would have lattice energy that is 4 times as compared to the compound with the monovalent ions. I hope this is clear. Next time, if somebody tell you this, you should come up with the answer in a jiffy. All right. Now, if Z is same, okay, let's say now charges are same. For example, I'm talking about magnesium oxide, calcium oxide, and barium oxide. Then higher is the Re, lesser would be U. Why? Because your Re, the distance of separation appears in denominator. And otherwise also, it is easy to imagine, no, The further they are apart, the easier it is to separate them. All right. So MgO will have higher lattice energy as compared to calcium oxide, which would have higher lattice energy as compared to barium oxide. And not very difficult to imagine, because lattice energy is ultimately what? How easily you can break your lattice. Okay. And if you try to think about it, this is what melting point does. Now, melting of solid, what does it do? It tries to kind of melt your solid lattice. Okay. Somehow break some kind of bond. So melting point has got a direct correlation with the lattice energy. So that is why magnesium oxide will have higher melting point as compared to calcium oxide, which will have higher melting point as compared to barium oxide. I hope this is clear. So here I stop the concept of lattice energy. So this particular segment told you about the factors that affected the crystal structure, how the size affects it, how the bonding affects it, how the relative sizes of the cation and anion affect it. Okay. Then understanding the contribution and lattice energy. What is lattice energy and what are the factors that affect the lattice energy and what are the factors whom lattice energy affect? For example, melting point, etc. And then how we can qualitatively determine the lattice energy. All right. So I will stop this segment here and we'll go back to the structure, study some little more complex structure, and let's take a 2 minutes break here and let's hear from you what you have not understood or whether is there anything that you would want me to repeat. Anurag will go to chat box. How many people do we have? Okay. 10. 10. So is there anybody who has not done a solid state chemistry in their graduation or post graduation level? I hope most of you are research scholars here, or do we have postgraduate students as well? Okay. So Gunjan is in master second year. Is there anybody else who is doing MSc? And Gunjan, do you have a specialized course on solid state chemistry or materials chemistry in your coursework? Okay. So all this has already been covered for you? Okay. Okay, so maybe we can start the next section. All right. So in this particular section, we'll look at some of the structures that probably you would have studied, but it is always a good idea to do these structure because most of the solid state chemistry is based on uh, 3, 4 major structure, and there are some derived structure which are based on this structure. So if you have an idea of this, it makes life and your understanding a little easier. Okay. So first and foremost is perovskite, AbO3. Uh, Perovskite, basically they were discovered in Ural Mountains of Russia by the German mineralogist Gustav Rose. But in the honor of another Russian mineralogist, Perovsky, they were named. Okay. So perovskite, their general formula is perovskite is in fact, it is a wealth of, it is beginning of a wealth of structure. There are so many structures which are based on perovskite itself. So coming back to the basic perovskite, uh, its unit cell, there are two ways people actually try to visualize it. First of it is, and then we generally classify the two ways. I would not say two unit cell because a unit cell is same, but two ways you can visualize it, and they're generally classified as A type or B type, depending on whether you prefer to keep your A cation at the body center or B cation at the body center. But nothing is going to change because the coordination number, the structure doesn't know what you are keeping at body center or face center, right? It will only crystallize. It is how we try to understand them. So when we talk of A type, what we say is, now your A cation is a bigger cation, the biggest cation out of 3 ions you have here, 2 cations and 1 anion. Okay. So obviously its coordination number is highest. So in A type, let's say my yellow is A. So it is lying at the, look at the left hand side figure. A is lying at the body center. Okay. And if you have A at the body center, then your B will be at the corners of the cube. Okay. And your A's oxygen would be at the edge center. All right. Now, if we try to calculate my empirical formula given this unit cell, A contributes 1 to the unit cell. So I have 1 of A. Okay. There are 8 B at 8 corners, each corner contributing 1 by 8. So 8 into 1 by 8, we have 1 B. We have 12 oxygens at 12 edges, each edge contributing 1 by 4 to a particular cube. So 12 into 1 by 4, 3O. So that means my unit cell has got one formula unit of AbO3. I hope this is all right. If you go back and try to calculate the number of formula units of NaCl in rock salt structure, it will come out to be 4 formula units of NaCl in one unit cell. AbO3 has got one formula unit of AbO3 in one unit cell. All right. Now, if I try to visualize it by keeping B at the center, actually it is nothing. Let us try from here only. You move your attention. Let us not go to the right hand side figure. Let us try to understand from the left hand side figure only. Now, right now you had your concentration on yellow ion. Now, what you do is you go and concentrate yourself on this green ball that is at the uh, corner, the right hand side corner of this particular figure, that is this green ball. Okay. Now assume this green ball is the center of your universe. All right. So how many red balls are there around it? One. Okay. Then two. All right. Then there would be third ball here. Third ball here, then fourth ball at the back, fifth on the top, and sixth one here. So it has got 6 red balls surrounding it, and those red balls are nothing but oxygen. And how far those red balls are? If your lattice parameter is A, they are at A by 2. Okay? So that means if I consider my green ball at the body center, it will have an octahedron wherein each oxygen is separated from B by a distance of A by 2. Okay? Now, if you concentrate on this figure, this is your green ball at the center and you have 4 oxygens surrounding it by the distance of A by 2. Okay, so this is what we observed here. Now, how far are they? How many yellow balls are surrounding the green ball in this figure? See, there is one at the body center, and around each corner of this green ball, you will have 8 such cubes. So there will be 8 yellow balls which are separated by, now if I draw a line from this green ball to this front walla green ball, this is root 3a. So this distance is root 3a by 2. Now similarly, I have 8 yellow balls surrounding this B ball, surrounding this green ball at the distance of root 3a by 2. Okay, so that is how we can we can arrive at B type unit cell starting from A type unit cell. So when I talk of defining my ABO3 structure by B type unit cell, I say I have B at the center, I have 6 oxygens at the face center, and I have A at the corners. Okay. If I try to define it by A type unit cell, I say I have A at the corner, body center, B at the corners, and oxygens at the edge center. But now this was in terms of describing the structure as the unit cell. If I try to describe the structure as a space filling polyhedra, how will I say? Okay. You see all of these, whatever we just described, we know this structure has got BO6 octahedra. Okay. Now you concentrate on left hand side figure. Now this green ball is B. It has, suppose I'm concentrating on BO6 polyhedra of this green ball. This oxygen is one of its corner and this oxygen is associated to this green ball. Similarly, so that means if you try to imagine it 3-dimensionally, I can describe my ABO3 structure in terms of space filling polyhedra as corner sharing 3-dimensional network of BO6 octahedra. Okay. In fact, you can imagine if you look at this a particular cube, it is like, let's say you concentrate on this cube, each corner, each of the 8 corner is a center of an octahedra, BO6 octahedra. Those octahedra are joined by sharing corners and the BA atom sit in the center of those 8 BO6 octahedra. Okay. And now if you try to go and imagine, you can actually see that the coordination number of A, that is your yellow ball in left hand figure, in terms of oxygen is 12. It has 12 oxygens surrounding it. So we can say that your ABO3 structure is formed by BO6 octahedra and AO12 cube octahedra. All right. Okay, so this is how it is shown here. You can describe your structure either as corner share in TiO6 octahedra. If I'm talking of calcium titanate, their titanium is the B ion, or the phase sharing SrO12 or TiO12. I'm sorry, this was strontium titanate. Basically AO12 cube octahedra. Okay, now these are the coordinates for various ions. If I consider one of the corner of the cube as 0, 0, 0, then titanium lies at 0, 0, 0. Strontium, if I'm talking of, let's say, strontium titanate, where A is strontium, Strontium lies at half, 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 which is the A cation, and your oxygen lies at H center, which are given by half 0, 0, 0, half 0, 0, 0, half. Okay, there is yeah, all right. So I will just repeat, coordination number of A in terms of oxygen is 12. Coordination number of B in terms of oxygen is 6. All right. Now, here itself, I would try to explain you what is the ReO3 structure. Okay. Now, in terms of when we talked about cubic close packing, we said it is a close packing of, let's say, when I try to explain a structure of magnesium oxide, I say that magnesium oxide adopts the rock salt structure. What I say is, I say oxide ion form the cubic close packing, magnesium occupies the octahedral group. Okay. Now, when I say that my cubic close packing is formed not only by oxygen, by rhenium ion and oxygen ions, both in the ratio such that rhenium and oxygen are in the ratio of 1:3. Okay, that means now my cubic close packing itself is formed by ReO3. Then that results in the structure of the very famous structure which is called ReO3 structure. I can also apply the same formula to explain my AbO3 structure. I say that the cubic close packing is formed by uh, BO3, B atom and oxygen atom, such that ratio of number of B atom and oxygen atom is 1:3, and my A occupies the cubic site in ReO3. Okay, I hope this is clear. Now, perovskite structure, why do we study perovskite structure? Coming to something from a solid state chemist, you have a lot of elemental freedom. That means you can replace many number of A ions, any number of B ions, whatever you want to place. There is a lot of, this structure is highly flexible. Now, how is it advantageous? How does it matter to me that if I can replace any number of ions at A site or any numbers of ions at B site? This is because when I want to tune my property from a particular compound, if I want to add some properties to it, take out some properties from it, or modify it, if I would want to put a new element to it so that its properties are modified. But a particular type of properties, we should remember, is only supported by a particular structure. Okay. Now, maintaining the similar structure, I'm able to have elemental freedom. I can have variety of elements at that particular site. That is the beauty of the structure. That is the reason perovskite are one class of compound where you have dielectric, where you can have ferroelectric, where you can have relaxer ferroelectric, you can have conductors. See, one particular class where you have ferroelectric. Now, ferroelectric are basically insulators. And in AbO3 compound only, you have conductors. So, one particular class which can give you an insulator and a conductor also. That is the beauty of this class, which actually makes it very endearing to solid state chemists who are working on structure and property. Okay, now, all right. There is one thing about that. We just talked about in some, let's say, first half an hour, 40 minutes of the lecture, we talked about that the structure actually depends upon the radius of the cations and the anions that are occupying, that are going to occupy the particular lattice site. Okay. Now, in this case, in case of perovskite, there is a term which is called tolerance factor, or T. It is the one that decides whether the combination of your A cation and B cation will form perovskite or variants of perovskite. Now, in this case, they say that if your Ra plus Ro, that is radius of A ion plus radius of B ion, is equal to root 2 times of RB plus RO. That means it has to be 1.41 times larger than RB plus RO. In that case, your T is tolerance factor is 1 and you will get a cubic perovskite. Now, what is a cubic perovskite? Whatever we just studied about perovskite, A occupying the center, B occupying the corners, oxygen occupying the edge center. And all the octahedra are perfectly straight and joined and very nicely going. That is your cubic perovskite. That will happen only if the sum of Ra plus Ro is 1.414 times of Rb plus Ro. Now, suppose your Ra is smaller, okay? A cation is not exactly what I want from this equation. What will happen? Do you remember I told you the corner of the cubes are occupied by basically center of the octahedra? There are 8 BO6 octahedra that are joined. Now, if your A is smaller, and you also remember I told you that any condition wherein your cation is rattling in the site is not stable. So what will happen? These 8 BO6 octahedra, they will tilt to occupy the space because now the A that is lying in the vacancy has become smaller. Okay. Now when this tilts, your symmetry decreases from cubic to orthorhombic. Okay. This is why, I just tried to give you an example why you till now you would have studied that this depends upon tolerance factor. And if your tolerance factor lies between so and so, you have cubic. If it lies between so and so, you have orthorhombic. Beyond that, you have hexagonal. Beyond that, you have C-type and ilmenite. And higher than one, you have hexagonal. I'm only trying to give you a physical picture. Actually, what happens? Why does symmetry reduces? Okay. Again, telling you, you see, this is your cubic strontium titanate where corner of the cubes are occupied by BO6 or TiO6 polyhedra. And your A was big enough. But when that radius ratio decreases till 0.89, it is happy. It can still take A, even though A is becoming smaller. But below that, A becomes much smaller. Now it is rattling. So this octahedra, they tilt to occupy the space. When they tilt to occupy the space, the structure is no more cubic. It becomes orthorhombic. Okay, and beyond that, there is a range of structures. And above that, we get this kind of structures. Okay, so effect of size in perovskite is controlled by the tolerance factor. Tolerance factor is nothing but this particular expression, which is nothing but the relative sizes of your cation and anion. I hope this is clear. Now this takes a little more complicated form than your usual Ra by Rb because here now you have two cations and not one cation. All right. Okay. Then I told you that perovskite is basically, it is a khazana of structures. We have different layered perovskite also. And they are given special name based on who discovered it. Dion Jacobson, Rudliston Popper, Aurelius. Even though it is out of scope of this book, I'm only telling you so that tomorrow if you come across this term, you would have one thing in your mind. They are based on perovskite. For example, what is Rudliston Popper? Nothing. But you see this red layer? That means you have AbO3. These are corner sharing octahedra, which is nothing but AbO3. So you have 3-4 layers of perovskite, which are joined together by rock salt type of AO layer. Then again 3-4 layers of AbO3, then again rock salt type AO layer. So this kind of structure we can empirically define as AO AbO3N. And actually this N is the number of AbO3 layer which are interspersed by your rock salt layer. And this N also control the properties of the Rudliston Popper phase. Okay. Now, this is just one thing that I was telling you that how it is a delight of material scientists because you can go on varying the tolerance factor. That means you can go on varying Ra by Rb. And how can you vary Ra by Rb? You can choose different elements. Okay. So that will give you different structures within AbO3 and different properties. So it gives you a key to controlling, modifying, introducing new properties. Okay, and another interesting thing, when I talked about barium tightening, I say this adopts AbO3 structure. All right. Then I say NaTO3, sodium tantalate. This also adopts AbO3 structure. Then LaMnO3, lanthanum manganite. This also adopts AbO3 structure. What is the difference? 2 plus, 4 plus. Okay? 1 plus, 5 plus. All right? 3 plus, 3 plus. That means you do not just have the possibility of introducing different ions, you also have the possibility of playing with the oxidation state. Given that the sum of the oxidation state of A and B is 6, you can have 2, 4, 1, 5, 3, 3. Okay, so it gives you immense scope to play with the composition, with the structure within same AbO3 by controlling the tolerance factor. Okay, so that is an interesting thing about the perovskite, and that is a reason this particular class of compound shows a variety of properties. Okay, so this is the superstructure based on perovskite, but I think we'll take a break here. We'll stop here, and please go and revise perovskite structure, if not the entire class, because next class I will tell you this structure of K2NiF4 or La2CF4 or Y123 oxide, which are superconductors, but based on perovskite structure. But for that, I would need you to have perovskite structure right at the back of your mind. Okay. So we'll take on from here in the next class, and please come up with any doubts. If you have any structure that you have not in this class, but you studied somewhere else and you would want to know more about it, please write to me so that, if I know, I will tell you right then and there, or else I'll go and read about it and then we can discuss. Okay. PDF for what, Ankur? Okay, ALBR3 structure. Sudhi, what I wanted to say is ALBR3, if you ask anybody and if you go back to your 12th or I don't know when did you read it in organic chemistry, it exists as Al2Br6 dimer. Okay, because it is a covalent compound. On the contrary, ALF3, it exists in a crystalline form as an ionic structure. What I wanted to tell you is that it's not that the covalent solid we cannot explain based on close packing. We can still explain based on close packing. Anurag, I need to open up the PPT, the second lecture. Okay. What I wanted to tell you was that ALBR3, when you want to, ALBR3, when you want to explain it as CCP, close packing, we can say that its bromine ion are forming hexagonal close packing. That is AB type. And aluminium ion are occupying 1/6 of the tetrahedral hole. Okay, we can explain it in terms of close packing also. We can explain ALF3 also in terms of close packing, but there all the fluoride were equally bonded to each other. That is why it was a high melting solid. ALBR6 का problem क्या है कि even though इसको भी हम close packing के terms में explain कर सकते हैं, problem क्या आती है, ये जो Al2Br6 यूनिट है उसके अंदर बॉन्डिंग स्ट्रॉन्ग है एंड देन अगली Al2Br6 से इसका even though ये साथ साथ hexagonal close packing की terms में I am explaining it, but still they exist as Al to Br6, where Br from one Al to Br6 is not as strongly bonded to Br from other Al to Br6 as compared to what it is bonded in Br in its same group. Okay, so and this figure only tries to relate your hexagonal close pack bromine with how the dimeric unit is existing in it. So basically, if you concentrate on the right hand side figure, these are all bromine ions in HCP layer. Okay, so basically it is the darkened one is your this thing, first layer, and then the shaded one is your second layer. So here, if I see actually uh, 1 and 2, you can relate from the layer lying downward. Then 4 and 5 are on the basically the second layer. So this is how 1, 2 and 4, 5 are basically first, I'm sorry, 1, 2 and 4, 5 are lying in the first and the third layer. So they are AA layer. And 3 and 5 are the center layer, which is actually lying on the triangular wall. So 1 is lying directly over 4, 2 is lying directly over 6, and 3 and 5 is the bridging bromine of the Al to Br6 unit. Okay. Similarly, 1, 2 ke baju mein, if I can tell you, this 7 and 8 are also there, right? Similarly, आपके 4 और 6 के बाजू में ये dotted 9 भी है, लेकिन 6 is not bonded to 9 as strongly as it is bonded to 4. Similarly, 7 is not bonded to 2 as strongly as it is as 2 is bonded to 1. So even though I can explain Al to Br6 structure also based on close packing, but in that close packing, the bonding between the dimeric unit is much stronger rather than the three-dimensional bonding. So here, that is why this particular structure is weaker as compared to ALF3. ALF3 being more ionic, will have a more three-dimensionality, will have more crystalline structure as compared to Al to Br6, because Al-Br bond has got more covalency, because bromine is a bigger and a more polarizable ion. उसका electron cloud बहुत बड़ा है, covalency आ जाती है, तो rather than forming bond and with all the bromines and getting a higher coordination number, it would rather try to restrict itself as a dimeric. This is what I wanted to say. Okay. Okay, so I hope no more questions now. Since I would anyway be continuing with the structure in next class also, as I said, any doubt, ask me. You come across any structure which I will not cover, please ask me. If I'm able to explain then and there, I would be very happy. Otherwise, I'll go do my homework, get back to you. Okay. And after the course also, you have my email ID. So please feel free to contact me. In this process, I also learn a lot. So we'll end up here. Thank you very much. Good evening. And I'll meet you on Monday now. Thanks.